Yeah. So in the last class, while finishing, we were talking about this translation vectors and primitive translation vectors and primitive unit cell. And we defined the primitive unit cell as the smallest volume cell whose sides are going to be A, B, C. And this A, B, C are called the primitive translation vectors. And the directions of A, B, C would be defining the crystallographic axis direction for that particular crystal. And we saw that it is called primitive because there is only one lattice point associated with that unit cell. And we saw a figure where we talked about the difference between a primitive cell and a non-primitive cell. We have shown here that in this picture, the last A is actually a cubic cell, which is primitive. But on the right, you have a body-centered cube, which is non-primitive because there are actually two lattice points associated with that cell. And by the way, I made a mistake in the last class. I think I just want to mention, I don't know how I just said that. When I was talking about the number of, where is that? The number of atoms associated with face centered, I guess. I was talking of face centered at some point, and there I have mentioned. Let me check where is that slide. Yeah, when I was talking of so 8 into 1 1 by 8, that is 1, that is fine. I did remember making a statement somewhere about about FCC. In FCC, the number of atoms per, or the number of lattice points per unit cell is going to be 1 by 8 into 8 plus half into 6. This is a mistake I made. It is half into 6 because there are only 6 faces. Half into 6. Surprise, nobody pointed this out. Okay, so 1 by 8 into 8. So they are the 8 corners. And when you come to the face, okay, so one lattice point is shared by 2 such cells. So it is half into 6 because there are only 6 faces. Okay, so that makes it 4. So this was a mistake I made. I don't know, later I suddenly remembered that I had said this to you. Okay, now let's just go ahead. And I will be introducing a term called, Wigner-Seitz cell. Wigner-Seitz cell. A Wigner-Seitz cell is a primitive cell. For any crystal, any kind of a lattice collection given to you, you can actually create a primitive cell. You can actually create a primitive cell, and it will be easier than what we have shown in the last class. In the last class, I have shown you the creation of primitive cell for BCC and FCC, and then talked about the angle A, B, C, and all that. That's slightly difficult to understand, but then there is an easier way of doing it. Okay. And so what you get at the end of it is called a Wigner-Seitz cell, and Wigner-Seitz cell is a primitive cell, meaning it's going to have only one lattice point per unit cell. And it's called Wigner-Seitz cell because it's named after the person who came out with this creation. Okay, so he created this concept of construction of a primitive cell. So how do you actually do it? So as mentioned in the last class, it is difficult to visualize things in 3 dimension. So we will do it in 2D. So here, are you able to see these dark dots? So these dark dots are actually the lattice points for the given crystal. Okay, and then I have just used a pen and then drawn a red parallelepiped just to show you how the A and B are going to be there. Just that's all, nothing more than that. It has got nothing else to do with this particular figure. I just drew it for you to see how A, B looks for this particular cell. And it's a 2-dimensional cell. But now I want to create a Wigner-Seitz primitive cell. So what I will have to do is take a central lattice point. Whenever such a construction has to be done, take a central lattice point and connect it to all the neighboring lattices. Connect it to all the neighboring lattices. So here you see 1, 2, 3, 4, 5, 6, 7, 8. So this central lattice point, you're going to connect it to the neighboring lattices. After you connect, what you have to do is draw a perpendicular bisecting plane. Draw a perpendicular bisecting plane. In this case, it is a line. Here it is a line because it's a 2D picture. But then if it's a 3D picture, what you have to do is you have to put a plane, a perpendicular bisecting plane. So you see here, this is cutting this distance into 2 and then drawing a perpendicular bisector. In this case, it's a line because it's a 2D. So like that, you have to do for all the lines joining the central lattice point to the neighbors. Then once you do that, the figure that you get, the resultant figure that you get, a closed figure that you get is going to be your Wigner-Seitz cell. The closed figure that you get here, okay, is going to be the Wigner-Seitz cell for this two-dimensional crystal. Similarly, if you're talking about a 3-dimension, then what happens? Okay, let's say this is one axis, so I have to draw a perpendicular bisector. Similarly, for this axis, draw a perpendicular bisector. Similarly, for this, like this, for all the lines, you just make perpendicular bisectors. Then what you get is going to be a closed 3-dimensional surface, which you will be calling as the Wigner-Seitz cell. Now, the difference between a normal primitive cell and this cell is going to be that in a Wigner-Seitz cell, you will find that there is only going to be one lattice point, and that lattice point will be at the center of the Wigner-Seitz cell. Now you look here, in this picture also, you're seeing that there is only one lattice point per cell, and where is it located? It is located at the center of the cell. So did you guys understand what is a Wigner-Seitz cell and the construction? You want me to repeat?
Yes, ma'am.
You want me to repeat? Okay. So last class we saw what is a primitive cell. So primitive cell can have lattice points at the corners and all that. It's slightly complicated. So we are going to find out another way of creating primitive cell, that is by geometric construction. And this kind of a cell that you create is called the Wigner-Seitz cell because it's named after the person who did it. So what you do here is you have to take, so let's say I have lattice points like this. Okay, I'll show you another construction. 1, 2, 3, 4, 5, 6. Okay, let's say this is my construction. I take the center one and connect it to all the neighbors. Connect it to all the neighbors and then draw perpendicular bisectors. Draw perpendicular bisectors. So the resultant picture that I am getting, a closed picture that I get, is going to be my Wigner-Seitz cell for this construction that I made. You can see that this is different from what the author has given. So that crystallographic orientations are also different. Okay, now instead of drawing a perpendicular bisecting line, if it is a 3-dimensional cell, you have to draw perpendicular bisecting plane. So when you have a plane like this, a plane like this, a plane like this, then what you get is going to be a closed figure. And where will be your primitive point? You will have your lattice point at the geometric center. Now, why are we talking of Wigner-Seitz cell? Our discussion of Wigner-Seitz cell will get over with this minute. The Wigner-Seitz cell is historically important in solid-state physics. The reason is Wigner and Seitz actually used this construction when they wanted to calculate the energy band and the energies, etc. You must have studied about band theory in your chemistry and in your SPM. Okay, so for the energy band calculation, the gap between the energy bands, they used this construction and then did it. That's of course out of the scope of your study, but then it's a historically important event. That's the reason why we talk about it here. Okay, now we are done with that. Now let's move to another part of the chapter. So when we are talking of crystallography, there are some things that you need to definitely know. One is the unit cells we just discussed. Next thing is there is something called symmetry and symmetry operations of unit cells. Now, an understanding of the basic unit cells, the symmetries, symmetry operations, all this will help you in understanding crystal structure better. So we will now start discussing on symmetry operations. So what is a symmetry operation? I do a certain operation, and after that operation, if the object looks as it was at the beginning, I do an operation, and after I do that operation, if that object looks exactly how it was before the operation, then such an operation is called a symmetry operation. Like, for example, if I'm going to take this cell phone, I have an axis here, and if I turn it by 360 degrees, unless you saw me turning it by 360, you don't know that I did this operation of turning it by 360. To you, it looks exactly how it looked in the earlier picture. Okay, so these kind of operations are called symmetry operations. So in short, you can say that an operation that will take a crystal into itself is called a symmetry operation. Now, there are three types of or three classes of symmetry operations. The first is called the translation operation. Translation operation, as the name itself suggests, you will be going from one lattice point to another lattice point through a series of steps. So that is translation operation. The second is point operation. It will be the operation that you do will be about a given lattice point. So that's a point operation. The third is hybrid operation. Hybrid operation is a combination of translational operations and point operations. So let's start off with translational operation. Translation operation you've already seen in the previous class is if I have a lattice point here inside a crystal and I have another lattice point here. In going from a lattice point R to R prime, I can only go by using a translation vector so that R prime is equal to R plus T. Okay, and we have seen what is this T. T is the translation vector given by N1A plus N2B plus N3C. Okay, N1, N2, N3 are integers necessarily, and R prime and R are both going to be lattice points which are identical. This is a translational operation. Okay, now before we go to point operation, I have to introduce a term called Bravais lattice. In SPM, you have studied Bravais lattice. In chemistry, you have studied Bravais lattice. Yes or no?
Yes, yes.
You have heard. Okay, so can someone tell me what is Bravais lattice? Anyone? A Bravais lattice is simply a two-dimensional or a three-dimensional basic structure. Okay, a two-dimensional or a three-dimensional basic structure which consists of some lattice points, and all the lattice points are going to be equivalent. That is, if you have a basis at one lattice point, the same basis will be fitting all the lattice points. Then you will ask, Madam, this is what you have been telling for the last 2 days. Every lattice point is identical and every lattice point will have the same basis. This is what you have been telling. Yes, I am saying that because we are in the preliminary stages. So when we are going to deal with those kind of an explanation of lattice, any two-dimensional or three-dimensional fundamental structure which can be used to generate all kinds of crystals are called Bravais lattices. So a Bravais lattice is a fundamental space lattice of a crystal where all the lattice points involved are going to be identical. They have the same basis. There are some things called non-Bravais lattice also. In non-Bravais lattice, all the lattice points are not equivalent. There can be some basis in some lattice points and there can be some other basis in some other lattice points. Okay, I hope you understood what's the lattice, Bravais lattice now. If, for example, I draw one structure and I put Na at one point, Cl at one point, and then call it a Bravais lattice, it is not a Bravais lattice. Meaning, if I put Na at one lattice point and Cl at another lattice point, then they are not equivalent. Okay, the Bravais lattice means every lattice point is equivalent. And they are fundamental building structures. So if you see how many such Bravais lattices are there, you will see that you're going to see that there are 5 two-dimensional lattices and 14 three-dimensional lattices, using which you can actually generate any crystal. So before I just wanted to introduce the term Bravais lattice here, but now we are going back again to operations. First we finished the translation operation. Now let's get into the point operations. So as I said, point operation definitely means that there is a lattice point around which the operation will happen. Okay, so operations at a point within the Bravais lattice. Point operations are operations at a point within a Bravais lattice. So let us see some examples of point operations. The first is going to be a mirror reflection. The first is going to be a mirror reflection. So this is my point in my lattice about which I'm going to see what kind of symmetry is there. I can see that if I put a mirror like this, a mirror M1, what is on the left-hand side is the same as what is on the right-hand side. What is on the left-hand side is same as what is on the right-hand side. So that means we will call this plane as M1. We'll call this plane as M1. Okay, so M1 is a symmetry plane. It's a symmetry plane. Similarly, this structure has got two symmetry planes. M2 is also a symmetry plane. Similarly, we may be talking about M3 also. Okay, now, whenever you are talking of a mirror reflection, and when you're talking about the type of mirror reflection, you have to write M. M denotes mirror reflection about a lattice point. And after the reflection, the structure remains undisturbed. So that's why we say that such a crystal has got a reflection symmetry. So you have a plane about which you are reflecting. This side of your crystal is the same as on the other side. Now let's move to another point symmetry called inversion. So look at this picture here. I have some lattice points. I have a lattice point O and I have a lattice point A. So if I can see that the position vector of lattice point A with respect to O is vector R. Now at minus R from O, this is at R you have a lattice point A. At minus R, if you have another lattice point, at minus R, if you have another lattice point, an equivalent lattice point, then you say that this crystal is having an inversion symmetry. Again, I repeat, I have a lattice point A. So I find that at a vector R from O, I am having a lattice point A. Now, from O, if I take a vector minus R, and if I find a lattice point, identical lattice point there, then I say that this crystal is having an inversion symmetry. And this lattice point O is called the center of inversion. Similarly, one can talk of rotation. So when we are talking of rotation also, necessarily the axis of rotation should pass through a lattice point. So if there exists an axis passing through a lattice point, and keeping this as the axis, if you rotate the crystal by some 2 pi by n, and n can be 1, 2, 3, 4, and 6. Look at this. N can be 1, 2, 3, 4, and 6. 5 will never bring the crystal to its undisturbed position. Okay, now look at this. What does this mean? Let us see. If n is equal to 4, here in this picture we have given n equal to 4. N equal to 4 means what? What is 2 pi divided by 4? What is that angle? 2 pi divided by 4 is?
90 degrees.
90 degrees. So, by a series of, when I turn it by 90, I'm able to get the original structure. When I turn it by another 90, again I'm getting the original structure. If I turn it by another 90, I'm able to get the same structure. If I turn it by another 90, I'm coming back to the original position. So that means there are actually n equal to 4 number of positions where there is a symmetry for this particular crystal. Okay. Similarly, there will be some crystals, which don't have this kind of symmetry. Like, for example, if I have A not equal to B and the angles are all twisted and it is some funny figure, then what happens is, I have to turn it by 360 degrees. That will be the symmetry of rotation. Okay, only one. So I have to turn it completely once for it to look exactly how it was at the beginning. Now look at the next picture. That's a hexagonal structure. It's a hexagonal structure. Okay, you can see that by turning it by by turning it each time by 2 pi by 6. What is 2 pi by 6? 180 by 6 is 30 degrees. Each time by turning the crystal about that axis by 30 degrees, you won't be able to recognize whether you have turned the crystal or not. It's going to look exactly how it was at the beginning. So like this, I can actually turn it 6 times. So that means this crystal has got a 6-fold symmetry. So again, I'm repeating 1-fold symmetry, 2-fold rotational symmetry, 3, 4, and 6. 5 is not there. 5 will never bring a crystal back to its original position. Now this axis about which you're rotating is called the axis of symmetry, and the number of turns you have to make, the number of turnings that you give till you reach that original position is called the number of folds. So it's n-fold. If you have to, if it's possible for you to have 4 turnings and yet keep repeating that crystal, then it is called 4-fold symmetry. Is this clear?
Yes.
So a sphere will have how many folds symmetry? I have a sphere.
0. I mean, 0 or infinity. Like
Infinity. But of course, a sphere is just an object. It's not a crystal.
Yeah.
But so in crystallography, you can have only this. Now I asked the question to know whether you understood what is the meaning of symmetry, rotational symmetry. Okay, so now let's go to hybrid operations. So let me again take you back. So in point operations, what all did we see? Mirror reflection we saw, then we saw inversion, then we have seen rotation. And in translation, just translation. Now we'll go to hybrid. So what are hybrid operations? Hybrid operations are combinations of these. Combinations of these are called hybrid operations. Okay, so the first thing we are going to see is rotoreflection. Rotoreflection, as the name itself says, it is a rotation. Okay, this is going to involve a rotation. Let us say some n-fold rotation. A rotation and a reflection at a plane perpendicular to the axis. If this is my axis of rotation, then the plane has to be this. The plane will be perpendicular to the axis of rotation. Then it is rotoreflection. So whenever you are having a crystal is having such a symmetry, this is the way you will express it. N/M. Okay, N can take, as I said, 1, 2, 3, 4, or 6, depending on what is your crystal structure. And M, again, M, whether it is M1, M2, that you have to see the crystal and decide. But then you give it combination this way, N/M. Here is an example of a rotoreflection, 2/M. 2/M. Look at this. 2 means what? I have a lattice point here, let us say. I have a lattice here. So I'm going to turn it by 180 degrees. If I turn this by 180 degrees, my lattice point will go from A to the point B. Fine? 2 pi by 2 means my lattice point from A, it will move to B. Is that fine?
Yeah.
Yeah, and this is my axis of rotation, symmetry axis. Okay, and after I have rotated it, I'm going to reflect it. reflect it about a perpendicular plane. So this is my plane of reflection and I have reflected it. So when I reflect, what I get is A prime. So what happened? From A, you got A prime by a series of two steps. One is a rotation followed by a reflection. So this is called a rotoreflection. And if you see the final picture, you see here A and A prime. Is it not what we have seen previously as inversion operation? So this is an inversion operation. So an inversion operation can be seen as a combination of a rotation and a reflection. Again, I'll tell you, in case you're wondering why you're studying all this, we will stop our studies with this in the next 2-3 minutes. So these are some basic things that you have to know. But then really understanding crystallography itself is an ocean. To really understand crystallography, you have to do much more than this. You need what is called group theory. Have you heard of group theory in mathematics?
I've heard of it.
Heard of it, yeah. So that's actually a higher level mathematics. So that will come into picture when you have to study crystallography. So we are just going to touch the surface. You're just BSc students. In fact, normal BSc students, they don't even do this much. Okay, now let's see what is roto inversion. This is another hybrid operation. So here what happens is you have an n-fold rotation followed by an inversion. So let's try to draw the picture and see how it looks. Roto inversion. So I have a lattice point here, I have a lattice point here, I call this A, I call it O. Let's say I'm going to, this is my axis of rotation, let's say I'm rotating it and let's say it's twofold, so I'm getting my A prime here. But then there is an inversion, it's not a reflection, it's an inversion. So if I do an inversion, I get it here. Okay, so A rotated to A prime inverted to A double prime. So this is the operation. And you can see that this operation could as well have been a reflection. It could as well have been just a reflection. Okay, so this is roto inversion. See here, because it's a plain sheet, we are showing 180. But instead of 180, think how it will be if it was 90 degrees. If it was 90 degrees, the picture would be more complicated. Or if the picture is a 30-degree rotation, picture will be more complicated. Next, let us go to a third hybrid operation. So that's screw translation. A screw translation is you're going to have an axis, you're going to have an n-fold rotation followed by a translation parallel to the axis. Again, repeat, a rotation followed by a translation parallel to the axis. Then it is called screw translation. Previously, we have talked about a rotation and a reflection with a plane perpendicular. Okay, whereas here we are talking about a translation parallel. So let's see here, you have a point. Okay, you have a point here. So this is A. So let's say this is the first operation. You're rotating it. Every time we are taking 180 only because twofold we are taking because it's a two-dimensional picture for you to understand. Okay, but then you can have 2, 3, 4, etc. So this is the first operation, rotation, and after that you're doing a translation and taking your lattice point here. Or after you do this, if you find a lattice point there, then you know that this particular crystal is having a screw translation symmetry. Symmetry where n is 2 and you're able to do a translation. Then of course there is something called a glide reflection. A glide reflection is a reflection and a translation parallel to the reflection plane. So if this is my reflection plane, I do a reflection, okay, and then a translation parallel to that plane. Then it is called glide reflection. Then finally, there is something called an identity operation. Identity operation means you're doing nothing. Identity operation means you're not doing anything with that crystal. You're just keeping the crystal as it is. That is called an identity operation. Then you will ask, why do you need an identity operation? For that, I'll just try to
Why
give.
an operation? Okay.
Exactly. You got it. That is for an operation. Like for example, when we are talking of matrices, operating matrices, you do use identity matrices. Okay, so in group theory, you would see that, I don't know, that is if you do that kind of mathematics and physics, you will see that this identity operation is actually going to help you do these operations. So that's the reason why, to give a mathematical formulation of this entire thing, you have this identity operation. Okay, so that's just to meet the requirement of group theory, and it equips physicists to do your quantitative calculation when you're talking of the properties of crystal and then connecting it to the symmetries. I'll just give you an example. What is the word? I'm not getting that. There are some properties, you studied this again in SP. There are some properties of material which don't depend on the direction. There are some which depend on direction. Can you tell me what are those two terms? Properties that depend on direction, properties that don't depend on direction. Anyone? Isotropy, non-isotropy. Have you heard this?
Yeah.
Right. Isotropic properties and non-isotropic. So I'll give you an example. Many times in superconductors, for example, what happens is, I'll just draw a picture and show you. You will have structures like this, A, B, and your C will be much larger than A and B. C will be much larger than A and B. Okay, so in these cases, what happens is, the bonding, or why go all there? Let's even take the example of your graphite itself. In your graphite, why does graphite slip so easily? Because they are sheet-like structures. Yes or no?
Yes, hexagonal sheets.
Right, graphite, it's sheet. Okay, similarly, some materials, they show a tendency to be cleavaged. That is because of the kind of bonding and the distances between the atomic layers. So you are able to connect a property to the crystallography. Okay, so that's the reason why, you need this group theory and an understanding of crystallography. But most of us, that includes me, in our experimental physics, we really, because we are not crystallographers, we didn't really get into this. Like for example, my PhD was on superconductors. I make a material, then I have to find out whether this material is really of that crystal structure. So what we do is we used to put that sample through a process called X-ray diffraction studies. When you do that, diffraction from various planes will happen, and then you get a pattern. And by studying that pattern, you are able to calculate your A, B, C parameters, and then what is the angle. You actually try to understand what is the crystal structure that you have got. To that extent, we have already used. We are all, none of us, for that matter, in HCU, chemistry and physics department, there is nobody who is an expert on crystallography. That's a field by itself. So here, the attempt is only to make you understand that such things are there. So where do you do all these symmetry operations? That's the next question. All these symmetry operations that we discussed till now will be done on Bravais lattices. And when you do it on Bravais lattices, they lead to different types of crystal structures. I again repeat, all these operations, symmetry operations that we discussed and combinations of symmetry operations that we discussed, everything is done on the Bravais lattices. And when you do it on the Bravais lattices, the resultant that you get is going to talk about the symmetry of that particular crystal, or you're able to generate all possible crystal structures by just doing this. So this is just a repetition. What is a Bravais lattice? So you have actually 5 2D Bravais lattice and 14 3D Bravais lattice. Then you will ask, where does, you have been talking about 2D lattice from the last 2 days. Where do 2D lattices exist? Will be the question. 2D lattices may not really exist. First reason why we talk about 2D lattices is because it is easy to visualize. Okay. And if we understand what is happening on 2D, then understanding what is happening in 3D becomes easier. Straight away, if you go with a 3D picture, it becomes difficult for you to understand. That is one reason. Then you will ask, does it mean that 2D has only academic interest? No. 2D also comes into picture in situations like what I just told you a few minutes back. I'm talking about a small A, B, and a large C. So there what happens is, each sheet behaves like a 2D structure. So it's not as if, they don't really exist. They do exist in these forms. Or if I'm talking of nano materials, we have one dimension, we have two-dimensional materials. So there also you can talk of 2D. Then I'm going to introduce two terms. One is called the point groups and space groups. Point groups and space groups. What are they? Let us see. A crystallographic point group is a set of symmetry operations. It's a set of symmetry operation that leaves at least one point of the Bravais lattice unmoved. I have a Bravais lattice. At least one point, lattice point of that crystallographic Bravais lattice should not have moved after your operation. Then you say that a collection of such operations are called point groups. And there are 32 crystallographic point groups. And how do you know that the given Bravais lattice is having those symmetries or 32 point groups? Which of the 32 that particular Bravais lattice is having? How do you know that? So you can know that by doing symmetry operation. Point group detection is done by rotation and reflection. By doing rotations and reflections, if you are able to, various types of rotations and reflections you do, and if you are finding that the Bravais lattice remains unchanged, then you know that these are the given crystallographic point groups associated with that particular Bravais lattice. Similarly, you talk about something called space groups. What are space groups? You're going to see that there are 14 Bravais lattices. You've studied it in chemistry, you've studied it in physics also, you've studied it in SPM also. So if you take 14 Bravais lattices and you do this combinations of 32 point groups, which I just explained, can be done. Not everything on all the Bravais lattices. Certain Bravais lattices can accommodate certain point groups. So by doing these combination of symmetry operations, okay, you will be able to generate all possible crystals. You will generate all possible crystals. Okay, now there are 230 space groups possible. Okay, and how do you know that a particular space group is possible for a given Bravais lattice? So what are the operations which will help you identify? The operations that will help you identify will be rotation, roto-inversion, your reflection, screw axis, glide axis, symmetry operations. All these things, if they are able to show you, they will help you identify which of the space groups is associated with the given Bravais lattice. Okay, now let's talk of crystal types. So first let us talk of 2D crystal types. Okay, why discuss 2D crystal lattices that I already discussed? I'm not going to touch that. You will find it in green letters at the bottom of the page. So first of all, let's start off with two-dimensional crystal lattices. There are 5 Bravais lattices that I told you about. Okay, of the 5, the first one is A and B. There is no restriction on A and B. A and B need not be equal and all that. There is no restriction on A and B and no restriction on the angle between them. Okay, so that is called a general Bravais lattice. That's a general Bravais lattice. And a general Bravais lattice can have only pi and 2 pi as the symmetry. They will remain invariant only under rotations of pi and 2 pi. And the axis obviously has to pass through the lattice point. Then this is one is over. Then 4 more we have to see. What are the other 4? The other 4 are based on the relationship between A, B, and the angle gamma between them. And the pictures are given here for you. Square lattice. Square lattice obviously means A equal to B and gamma equal to 90. So this is one Bravais lattice. Look at the next one. A equal to B and gamma equal to 120. This is hexagonal. A equal to B and gamma equal to 120. That is actually hexagonal. The next is rectangular. Rectangular, A not equal to B, but gamma equal to 90. Then the next one is centered rectangular lattice. Centered rectangular lattice. Okay. And the centered rectangular lattice here, you see there is a primitive shown and this is a non-primitive shown. This is non-primitive. You can see that it is simply the same collection of lattice points. Same collection of lattice points, but here you have drawn a primitive lattice. Here you have drawn a non-primitive lattice. And in this non-primitive Bravais lattice that you have drawn, you are seeing that you have actually not one lattice point associated with the cell. And it is called centered rectangular lattice because of this. Then 3-dimension. When you come to 3-dimension, instead of just A and B, you're going to have A, B, C. And they are called the cell parameters. And you can see that the angle between A and B is gamma, which we just talked about in 2-dimension. Angle between B and C is alpha, and angle between C and A is beta. So you have to remember this order. Okay, and the 14 Bravais lattices, we said 3-dimensional, 14 Bravais lattices are there, which can be divided into 7 classes. 7 classes. So let us just see what it means. What are the 7 classes? Let us see. This is 3-dimension. So 7 classes are triclinic, monoclinic, orthorhombic, tetragonal, cubic, trigonal, and hexagonal. So these are the 7 classes. I am sure you've seen this somewhere. Chemistry, SPM, you have seen this. So these are the 7 classes. And within these classes, you have triclinic is only primitive, number of lattices is 1, A not equal to B not equal to C, alpha not equal to beta not equal to gamma. Coming to monoclinic, A not equal to B not equal to C, alpha equal to gamma equal to 90, but beta is not equal to 90. Here what happens is, you're going to have a monoclinic what do you call that? Primitive, and B stands for base centered. You have a primitive and a base centered. Like this, you can talk of orthorhombic, tetragonal, cubic, trigonal, and hexagonal. The next, and one is supposed to know these axial relationships. One is supposed to know these axial relationships. Now look at this. This picture, everyone, everywhere, you have seen it. Okay, so this is one class. Here you're seeing that. So what did I first say? Triclinic and then monoclinic. So this is triclinic. You can say A not equal to B not equal to C, alpha not equal to beta not equal to gamma. Okay, what is the next one? The next one was monoclinic. This is monoclinic. You're seeing A equal to B not equal to C. Then you're seeing the relationship between the angles also. You're seeing that the one of the angles is not equal to 90. And you're seeing that this is primitive, whereas this is base-centered. Base-centered. And if it is base-centered, the number of, this is certainly not primitive, this is base-centered. And the number of atoms associated, you can check by yourself and see. Half plus half is 1 plus 1, therefore 2. 2 lattice points. But this is primitive, 1 lattice point. This way you could just go through and get what are all the 14 Bravais, 3-dimensional Bravais lattices. So operations on these, symmetry operations on these can generate any crystal. So in conclusion, the cell types are simple cubic, body-centered, face-centered, and then of course base-centered. So the number of lattice points associated with the cells are given to you. Cell volume is what I discussed last time. It is A dot B cross C. I'll stop here. So in the next class, what we'll do is we will talk about, this will be very short. We won't be repeating because SPM you studied a lot about lattice directions and planes. So we just touch and go. We should not be wasting time discussing this again here. The only reason why Bravis lattices was discussed here is when you discuss Bravis lattices in SPM or chemistry, nobody talks about the lattice points. People talk as if the points are occupied by atoms. That is not true. That's the reason why this is repeated here. Okay, so in the next class, we will start off with indices. Any doubts?
No.
Okay, I'll stop the recording.